Hi guys, it's your guy Olumide, and today we'll be solving another one of the most commonly asked tech interview question. It's the balanced binary tree validation. It's a commonly asked DSA question by top tech companies including Google, Amazon, Netflix, Meta, Apple, Microsoft, and other top tech companies. Right, let's go into the problem solving. The problem statement states that determine if a binary tree is height balanced, meaning no nodes left subtree and right subtree have a height difference greater than 1. And we are giving an example tree here. Look at this tree that you can see right here. For this particular tree, we see that it is imbalanced. Why? Because for this particular node 7, the left subtree is 0. What I mean is that this left subtree, let me look at to the left node of this 7. You see there is no node there, only the right node have 9 and the rest like this. So we see that it is 0, fine, but the right subtree, which means the right node actually have a height of 2. So and because of that, what I mean by 2 is because of this. Let me take this out now. So this is the first, this is the second. So why the left has 0? So, and because the height is now greater than 1, so there's a condition for a binary tree to be balanced. A binary tree is balanced if no node left subtree and right subtree have a height difference greater than 1. If no node left subtree and right subtree have a height difference greater than 1, but now a particular node has a height difference greater than 1 between its left subtree, which is 0, and right subtree, which is 2. And because 2 is greater than 1, it is not balanced. So one thing we can therefore realize is that for a binary tree to be balanced, all its subtree would need to be balanced too, right? Meaning that the left subtree and the right subtree of each and every node in the binary tree we need to have a height difference of no greater than 1. That is, it must be 1 or 0. It must not be greater than 1. Look at this, for instance, this particular node now, it has this left subtree and it has this right subtree. Now the height between this node and the left subtree is just 1. Let me say 1, right? Or, well, if I have to count it with this one, it's gonna be 2. If I have to include the node itself, this node itself, so it's 2. And at the same way, if I have to include this node, if I have to consider the right subtree now, it is 3. 1, 2, and 3. Now you see that 2 and 3 are just one difference from different from each other. So because of that, you can say that this particular node is actually balanced. Is a balanced one. So but for a tree to be balanced, each and every node need to be balanced, and because this particular one, this 7, have a left node of 0, well, if we are gonna be adding 7 to it, it's gonna have a height of 1, while the right node have a height of 3 when we add 7, the node 7 itself to it. And because of that, 3 is greater than 1, right? Or let me say 2 is greater than 0, right? And because of that, it is not balanced. So if one of the node is not balanced, then the whole tree is not balanced. Now this suggests that we need the way to determine the heights of the left and right subtree of each node, so as to determine if the subtree routing from that node is balanced. I mean, for each of the node, we have to determine the left and right subtree, and to ensure that the difference between the left and right subtree is not greater than 1, so we can be sure that, okay, at that particular node or at that particular aspect of the tree, let me say node, so the subtree of the left and right subtree is actually balanced, right? So we can then move on to the next node. So what we're doing in essence is that we're going to be considering and traversing through each node in the tree. Even starting from the root node, we're going to consider the whole left subtree. Concerning this root node, then we're going to consider the left subtree and we're going to consider the right subtree as well, and we are going to ensure that the left and the right subtree have no height difference greater than 1. So if it does not, we keep on traversing for each and every one. So if at any point in time, at any node, the left subtree and right subtree have a height difference greater than 1, definitely it is not balanced. But if we can loop successfully, if we can traverse through each and every node, and we can find out that the left and right subtree of each of this node does not differ greater than 1, definitely it is balanced. Now, a major insight is that the height of a tree is equal to the depth of its deepest subtree plus 1 to include the tree root node. What I'm trying to say here is that consider a tree like this now, this structure. So the height, if you go back to the introduction to tree that I discussed in my previous video, one of my previous video, when I want to start talking about tree, is in my YouTube channel and my other social media platform on LinkedIn, on Facebook, TikTok, and the rest of them like that. So if when we have a tree we have a height. Height is an attribute of a tree, right? And when we say the height of a tree, it's talking about the depth of its deepest subtree. What I'm trying to say is that considering this particular tree that we have here now, if we want to find the height, we just have to look for the deepest node, or let me say the deepest subtree plus 1. That is actually the height. Look at now. Okay, when we say depth, right, at this point, this root node, the depth is 0. Why? Because it does not contain any edge. When we say edge, these are edges. So, but because as a root node, it won't contain any edge at first because it is the root node, it is not connected to any parent node. So the depth is 0 at this point. Moving toward this next one now, the depth is 1. Why is it 1? Because there is now an edge. There's a up to 1 edge. So when we move on to the next node again, it's gonna be 2, right? So and that's why we have the depth to be 2. So now when we say we want to calculate the height of a tree, it's gonna refer to the longest, or let me say the deepest subtree, that is the subtree with the deepest depth, right? Because if you look into this second part, which is the right subtree, this is the left subtree, now this is the right subtree, you will see that the height is 1 because there's just one edge that is encountered until we get to the last node in the right subtree, right? And because of that, we see that if we compare 2 to 1, we can confirm that the left subtree actually have the deepest depth. So it's actually the deepest subtree, right? So now when we say we want to find the height of a tree, we just have to go and get the deepest subtree. Now that depth, I mean the length, what I'm trying to say in essence is the number. So the depth of that deepest subtree plus 1. So that one is to include the node itself that we excluded the other time because it does not have a parent, right? I said the node does not have a parent. This is not a node though. Don't mistake it for a node. I'm just trying to point it that this is a root node, right? So it's not a connection or edge. So it's just an arrow, a random arrow. So now after taking the depth of the deepest subtree, we just have to include plus it by 1. So that's what an height of a tree means, or the height at any node. You understand? The height. If I want to find this height of this one, so I'll just do the same thing. I'll just go and this is 1. The depth of this one is 1 because so far till we get to the end of the node, it is just 1 edge that we see. Similarly, here is just 1. So we can say that both left and right subtree have the same node, 1 1. So definitely the idea is that we go and find the left and right subtree, and the one that have the deepest subtree, the one that have the deepest depth is what we choose. So, and because both of them have 1 depth, we just choose 1 and we add 1 to it so as to include this node itself, the root node itself. So that's what brought us to this formula that height equals to 1 plus the maximum between the left height and right height. So where the left height refers to the height of the left subtree, and the right height refers to the height of the right subtree. So in this case, the height of the left subtree is 2 and height of the right subtree is 1. 2 is greater than 1, so maximum between 2 and 1 is 2, and then we're going to add it with 1, where 1 stands for this particular node itself. So really this formula could also apply to any node in the tree. So it could apply to this one too. So whereby the height of this particular node, the height will be 1 plus maximum between the left height and right height, so plus 1, which includes this particular node itself. So similarly to any node at all. So therefore we can see that this formula reveals a recursive relationship whereby we can keep on determining the height of the left and right subtree and trying to compare these heights together, so to see if they match the condition for a balanced tree. Don't forget that a balanced tree is balanced if the left subtree, the height of the left subtree and right subtree is not greater than 1. If their height difference is not the height, just their height difference. The height can be 5, 6, 7, but the height difference between the left and the right subtree must not be greater than 1. So in a situation like that, we can just traverse through the node of each node in the tree, right? And then we try to check if we try to calculate the left and the right subtree using this formula that the heights from any node. Consider this particular root node now. This is the left subtree right here. So right here. So you start from this point, right? And this is the right subtree starting from this point. So all we just need to do is to use the formula to calculate the height of the left subtree and calculate the height of the right subtree and to compare them to each other if they are not greater than 1. So if they are not, then we know that it is balanced. And the same way, just like we do the same thing for this root node, we're gonna repeat the same thing for this particular node here. How we can know if don't forget what I said earlier, that for a binary tree to be balanced, each and every node needs to be balanced. So we're not just comparing this root node alone, we are also comparing for each and every node here. So and then we are going to be checking if each and every one of them is balanced. For this particular node here now, it is balanced if the left subtree and the right subtree is not greater than if their difference is not greater than 1. Similar thing apply to this one if the left and the right subtree is not if their difference is not greater than 1. So we just keep iterating through each node in the tree and try to confirm whether their left and right subtree is not greater than 1. If it is greater than 1, definitely it is not balanced, but if it is not, it is balanced. Okay, considering the diagram on the screen, it actually displays the height that is returned from the left and right children of each node, and it shows us how to determine if a node if a subtree is balanced or imbalanced. Let's take a look at this particular root leaf node. I mean these two last node now. Considering this one here, you will see that it does not have a left node or a right node. It does not have both left node and right node, and so therefore if you want to look at the height of this particular node, I mean let's consider this particular node now, its height is gonna be 0 plus 1. Don't forget how we say we're gonna be calculating the height. It is actually the maximum 1 plus maximum between the left height and right height, where left height is actually the height of its left subtree and right height is actually the right height of the right subtree. Now for this particular node now, it has 0 left subtree and 0 right subtree. Why? Because actually the left and right subtree are none. There's no left, there's no right subtree, and because of that, so when we say maximum between left and right subtree, it's just gonna be maximum between 0 and 0, right? Because it does not have both any of them. So and because of that, when we say 1 plus that maximum, so it will be 1 plus 0, so the height of this particular node is 1. So that is the one that is gonna be returned here. So don't forget we need it here because to calculate the height of this particular node 4 here, we actually are gonna do the same thing, right? We are gonna be doing the same thing of 1 plus maximum between left height and right height. So we need the left height, which is 1, right? So that's why we are returning it. So it's a recursion. So coming here now, when we evaluate the right height of the right subtree, you see that for this node 4, it has a right subtree of 0. Why? Because there's no right subtree, right? And because of that, when we now look at this height difference, before we evaluate the height, one thing you need to put in mind is that before we evaluate the height of this particular one, of this particular node or any node, we first of all need to check if it is balanced at that point, right? Because there is no essence in determining the height at this node if the left and the right subtree is not balanced. I mean, if its left and right subtree is not balanced. So first of all, what we want to do is that we want to check if the difference between its left subtree and its right subtree is if it is no greater than 1, that is, if it is 1 or less than 1, if it is not greater than 1. So now the left subtree is actually 1, just like we see here, right? And the right subtree is 0, right? Because it doesn't have the right subtree, so its right subtree is 0. Now the difference between 1 minus 0 is just 1, so it is not greater than 1. Because of that, fine, it is at this point, up to this point, it is a valid binary tree, and because of that, we can proceed to find the height of this particular tree. And now we can find the height is just by taking the maximum between 1 and 0, because its left height is 1, height of the left subtree is 1, height of the right subtree is 0, sorry, and then we just have to do 1 plus that. So but what makes us do this is because we are sure that it is a valid binary tree, it's a balanced binary tree, because the difference between the left subtree and the right subtree is not greater than 1. So, and at this point now, we can conclude that the height of this particular tree is 4, of this particular node. I mean, the height downward is 4, right? Because we are doing 1 plus maximum between 1 and 0. So same thing apply here. Sorry, the height is 2. The height is 2. I think I said 4 is 2. So, and because of that, you see that we returned 2 upstairs here as well. We return 2 to the parent node. So meaning that what the height of the right node of this particular parent node 2 is 2. I hope you understand me. So, and therefore, if we do the same thing to this particular left node now, that you can see here, the height is gonna be 1, right? Because it has no left node and right node, so the maximum between the left node and right node is 0, and 0 plus 1 to include this node itself. What does not make it 1? So that means that the height of this particular left node is 1, and the height of this particular right node is 2, and because of that, we are gonna first of all check if the difference in height between the left node and the right node is not greater than 1. If it is not, fine, we can proceed to find the height of this particular node 2 itself. I really hope you understand what I'm saying. I really hope so. And because of that, let's continue. When we now try to check, we say that 2 minus 1 is actually 1, right? So meaning that it is balanced. The height of this left node is 1, the height of this right node is 2. It is not greater than 1. The difference is not greater than 1. Because of that, we proceed to calculate the height of this node, particularly this parent node, that is a parent node to the left node and to the right node. And to do that now, we just have to take the maximum between the left node and right node, which is definitely 2, and we are going to add 1 to it, and that's why we have this 3 right here. So, and because of that, this further implies that the height of the left node to this parent node 5, which happens to be our root node, is 3. You see, and because of that, we now proceed to find the height of this right node here. I mean, since we already know that the height of the left node is 3, we need to find the height of the right node and compare to check if it is balanced or not. So what we're gonna be doing is that, don't forget how we solve this, right? We start from the bottom. So that's the easy way whereby you can use to know the height, bubbling the value up like that. So because of that, don't worry, DFS is gonna help us to take care of this. DFS know how to traverse an array from the bottom. Don't forget, if you follow my previous videos, you will know that we have DFS, which is the depth first search method, and the BFS, breadth first search method. You can check it in my YouTube channel, right? Okay, so starting from this bottom again using DFS, it's just a simple algorithm that we're gonna solve it using DFS. So you are going to see it in this video. So starting from here now, the same thing apply. The depth of this one is 1, so 1 will be returned here. And now don't forget that this actually refers to the height of the left subtree, right? The height is 1. Now the height of the right subtree to 9, to 9 now, will be 0. And because the height of the left subtree is 1, right subtree is 0, 1 is difference between 1 and 0 is just 1. So up to this point also, it is a valid it is a valid subtree. And because of that, we are gonna proceed to calculate the height of the node 9. So, and to do that, we just have to take the same formula of maximum between left is 1, right is 0, so the maximum is 1, and we're gonna add 1 to it. That one is to include this node itself, this node 9 itself, so that means 2, and that's why up to this point what we do is to return 2. So now 2 happens to be therefore 2 happens to be the height of the right subtree to this node 7. Fine. But if you look at it, the height of the left subtree to node 7 is actually 0. Why? Because it doesn't have a left subtree at all. You see, it does not have it just have a right subtree of height 2. And because the 2 is actually greater than 0 by 2, you understand? So 2 is greater than 0 by 2, which is now more than 1. Definitely this is not balanced. This node is not balanced. And one thing is that for a binary tree to be balanced, every node, each and every node has to be balanced. So, and because it is not balanced, definitely we really need to return false. Don't forget that the output is false if it is not balanced, so we have to return a true or false to indicate if it is balanced or not. Right, okay. I hope you understand to that point. But one thing is that, we need to find a way of catching it once it is not balanced. Because if you look at it, right, if you look at it now, you will see that at this point you will see that even though it is not balanced, why? Because 2 is greater than 0 by 2. The difference is now more than 1. But still, if we proceed with our formula, we will just move on to calculate the maximum between left height and right height, right? And the maximum is 2. Then we will add 1 to it, and 3 will be returned here. And if we can cross that boundary, definitely 3 minus 3 is 0. There is no difference, so therefore it is still valid up to this point, and we might mistakenly return true that okay, this whole binary tree is valid. Why? Because when we apply the same formula to this point and to determine the height of this node, is gonna give us 2 plus 1, because the maximum between 2 and 0 is 1, right? And therefore it's gonna give us 2, and 2 plus 1 gives us 3, so it's gonna return 3 here. And because this left one, 3 is already waiting for us there, so it's gonna compare it and say that fine, the height is 4 and it is balanced. Whereas we just concluded now that it is not balanced because the height difference at this point, at this particular node 7, is more than 1. And so we have to find a way of returning false. And what we are going to do is that when we come here, fine, and we see that it is not balanced, what we are going to do is that we are not going to return 2. We are not going to return 0. We are not going to return the maximum between the left and right plus 1, just like we do. So instead of returning 3, we are just going to return minus 1 that we have here. So that way we are able to cache it. So we have applied the condition that if it is minus 1, then there is a problem, then it is not balanced, right? Because there is no how we want to calculate the height of any node of any tree to be 0 and to be less than 0, to be minus 1. You understand? So is either 0 or 0 upward. You understand? So it cannot be minus 1. So we sending in this signal of minus 1 indicate that there is a problem, it is not balanced. So when you see minus 1, then it knows that it's not balanced. So that is more that's more careful of us than to be sending in 2 or any other number that could be easily mistaken, right? So that's what we're gonna be doing here. That's what we're gonna be doing. And eventually what we'll be doing is that we'll just return false if the returned value is minus 1. So because that way is the way we've just concluded that we are going to cache it when we found something that is not balanced. When we find a node that is not balanced, we return -1. So whenever we return -1, we are quite sure that it is not balanced, so we are just going to return false. Alright, let's go into the code implementation to have a more deep understanding and implementation of the logic that we just described. Alright, let's dive into the code implementation for the balanced binary tree validation problem. Okay, first we'll be defining our tree node. So far I want to place an apology. I want to apologize for my previous videos. I've been mistakenly taking the graph tree node for graph node. It's actually a literal error. I actually mean tree node. Fine, we're gonna be talking about graphs, so but first we'll be considering trees. I mean the tree data structure. Graph is a different data structure. So in my previous video I used graph node. Just the same thing, just the only difference is that I'm using graph node instead of tree node. So it's supposed to be tree node, not graph node. So so sorry about that. I hope you understand what I'm trying to say. Like just by defining the class tree node like I'm doing now, you know, we are dealing with tree, right? The tree data structure. But I've been doing the mistake of writing graph node to create my as the class name in my previous video, so which is supposed to be tree node, and I don't think I can change it so easily like that. But it's just the same syntax, the same semantics, just difference in the name. Okay, we'll be doing similar things now by defining the class tree node, so which is gonna help us to keep track of our node, each node in the data structure, just like you can see in the diagram on the screen. So we have to replicate that structure in terms of code, so as to check if that particular structure is balanced or not. And we'll be using the tree node class to create our node objects. Alright, so these are the nodes that we'll be needing: node 5, node 2, node 3, node 1, node 9, node 7, node 6, node 4. So it's just how it is in the example problem statement. Similarly, this is their connection. Why I'm doing this is because this video is quite lengthy and I just want to do it snappy. So, and I hope you understand. I'm gonna do it in a way that you understand actually. So okay, we have this tree node here, which is node 5, right? So what we are doing down here is just to create the connection. You know, node 5 have a left attribute of node 2 and a right attribute of node 7. Node 2 have a left attribute of node 1 and right attribute of node 6. I mean, in the structure, we are just trying to clone that particular structure on the screen now. So by attaching the left and right attribute of each of them to where it is supposed to be. So you see node 9 also is connected to node 6 by their left edge or left attribute. So that's the structure in code format. Now let's proceed to define the function now that will help us to check if the binary tree is balanced. So we are going to be calling the function balance binary tree validation. It's going to be taking a node, so which is actually a tree node, and then it's going to return a boolean whether true or false, right? Okay, don't forget I can just call it now. Okay, let's just continue. I'm thinking of calling the function and passing in the node 5, which is the root node, but we can do that later. Okay, first of all we want to check if not node. So don't forget we'll be using the recursion format. I mean, we are using DFS to solve this problem now, and we'll be recursively calling from the root node. I mean from the leaf node. Don't forget in our code our logic that we explained, we are starting from the leaf node, and then from there we calculate the height, then we return that height to the top, to its parents. So that height will be the height of the left node and the right node. Then to do that we need to implement it recursively, and DFS is good for that. So we are using DFS method. So and what we want to do is that when we get to the leaf node, you know, when we get to the leaf node, say that node 6 for instance, node 6 is a leaf node now. So if you look at the structure, you understand that node 6 is a leaf node because it does not have any child. any left child or right child. So now if we now get to node 6 and we call this function on node 6, you see that node 6 does not have a left child and right child. So in situation whereby nodes a particular node does not exist. Okay, what I'm trying to say is that node 6 have a left child of none and a right child of none. That's what it means that node 6 does not have a left side and right side. Why? Because for each of the nodes that we created, we have initially set their left and right side. So it's either going to be a node or it's going to be a none. So if it is none, that's what if not node means. If it is a none, we just want to return 0. Don't forget the goal is to calculate the height. So at that point the height is 0, right? The height of that particular node is 0 because the node is none, so it doesn't have a height. So okay, fine. But if it do have a height, we want to calculate the left height, GIGHT. So we want to calculate the left height and the right height. And how we calculate the left height is just by calling balance binary tree of node dot left. So similarly, we want to calculate the right height by calling the balanced binary tree of node dot right. So well, you might be thinking that why do I have to recall this function? Fine. As we keep traversing to the bottom, right, it's gonna get to a point whereby is going to get to the non-node. What I mean by non-node is when you get to the leaf node, like node 6, whereby the left and right node is none. So it's gonna be able to return 0. So we can be assured that one day it's gonna get to the leaf node, it's gonna get to the non-node and return 0. So we are gonna collect any value which is 0 at first. So we're gonna collect it as 0 and write as 0, and then we want to check if left node, if the left height, if left height minus right height, fine, we have to collect it as an absolute, right? Why I say we should collect it as an absolute is because we don't know which of them. Left height might be 3, right height should be 5. Right height might be 5, left height should be 3. So we have to neutralize it by collecting it as an absolute if it is greater than 1. So at that point, don't forget what we say. We are going to be using this signal or indicator to show that okay, it is not balanced. Fine. So fine. Similarly, if left height is less than 0 or right height is less than 0, what we want to do is that similarly we want to return -1. So why we are doing this is because you see this is a recursion. So in the call to left, in the balanced binary tree validation call to node.left, it might return -1 as a result of the node not being balanced. Look at node 7 for instance. Node 7 is not balanced, so it's gonna return -1, right? So now after it return -1, we really need to check if the left height or the right height is -1. If it is less than 1, if it is, we want to return -1. We don't want to go further. Just like I told you that we don't need to go on to find the root node, to find the height of that node. We just have to, once any of them is -1, it signifies completely that the node is not valid, it is not balanced, and therefore the tree is not balanced. So you understand? If at any point in the node or at any point in the tree or at any node in the tree, if the node is not balanced and it returns -1, then we just want to keep returning -1 to signify that it is not balanced. So that's why we're doing this. So but if these two conditions does not happen, if the left node and right node is not balanced, or the left node is not less than, or the left height is not balanced, I mean if the left node and right node, if their difference in height is not greater than 1, and the left subtree is balanced, because the left subtree is going to be balanced if it is not less than 0, and the right subtree is balanced because right subtree is also going to be balanced if it is not less than 0, if it is not -1. So definitely if this condition satisfy, then this if statement won't work. if they are balanced. And in situation like that, we want to return 1 plus maximum between the left height and the right height. So 1 plus maximum between the left height and the right height, and that's just it. So it might look somehow, but see, to really understand all this problem including involving tree, you just need to understand the logic that I explained previously. It's very important, because really it might look so complex in code format now, but once you understand the logic, you understand how exactly to solve it without really disturbing yourself. So now it means that at any point, if it is not balanced, it's gonna keep returning minus 1 minus 1 minus 1 minus 1 minus 1 until and that's what it's gonna return. But if it is balanced, it's gonna return 1 plus maximum. So we can therefore we can then conclude that it's either we return a whole number, I mean a real number that is positive integer, or we return minus 1. So right, so if we return a positive integer, whether 0, whether 1, whether 2, we know that it is balanced. But if we should return minus 1 from this form, from this method, I mean from this function, it is not balanced. So now let's make a call to it. Let me say height is equals to balanced binary tree of node 5. So I'm gonna pass in node 5. So if height is greater than 1, if height is less than 0, so you can just, so I'm just simplifying the code. You can write it in one step. You can just say that return this if this, else this, but just let's do this to return false, else return true. Alright, is this given, is this syntax correct? Oh, sorry, we have to print. We are not in a function, so we are not going to be returning. We are printing, print this. So now this is simply how to solve this problem. So we call this function, it's recursively iterate through all the node from the bottom to the top. That's what DFS does. So we start from the bottom. So if you look at it, we are first calling the balanced binary tree validation on node.left. So it's gonna go into the left subtree and iterate through the whole left subtree before going to the right, starting from the bottom. So it's gonna go deep in. That's what we call depth first, and then later go up, go bubble up. So now let's run this code and let's see what happens in running this code, whether it's gonna return true or false. Don't forget, we expect it to return false. Why? Because at node 7 is not balanced. It has 2 nodes, 6 and 4, I think. So, or probably no, it has a right of 9, and that 9 has a right of left of 6. So, but the node 7 itself does not have any left. Because of that, it's supposed to return false. So you can see false is returned here in the terminal, right? So now I'm gonna do something. You know what I'm going to do? I'm gonna make it balanced by removing node 9 left attributes. I mean, so that it will just be node 7 right connected to node 9. So this is gonna be also let me get this out. So I'm gonna remove this. I hope you can see it on the screen as I remove it. So let's put it like this. So this way now is going to be balanced. Why? Because the difference between the left node, I mean from this node 7 now, the left node is 0, but the right node is now 1. I mean their height of the left node is 0, height of the right node is 1. So it's meant to be balanced. So let's see if it's gonna return true now. So you see I've removed it from the code too. I've removed node 9.left. So let's run this and see how it goes. We're expecting to return true. fine, it returns true. You see, it is balanced. You see, the code work well for when it's balanced and when it is not. So this is how to solve this problem. It is really long, and I'm so sorry for that. So I just want to make it more simplified so you can understand. Thank you very much for watching up to this point. I really appreciate, and do well to subscribe to my YouTube channel, please. More is coming, much more is coming. Thank you.